enthusiasm, great sense of humor, and really, really cute pictures of penguins. Please join me in welcoming Ken Goldman.
Well, thanks very much for that, Abby. I really appreciate that. And it's certainly a pleasure to be here. Thanks for inviting me. And it's a particular pleasure for me to be able to speak to Tahi School students and such great young people spending your summer doing science and math. That's very impressive to me. I never did anything like that myself. But anyway, so hopefully we can cool things off a little bit in here with such a hot day. Unfortunately, I didn't bring sea ice here to show you and maybe sit in the middle and cool everybody off. But hopefully in the video, when we actually travel to Antarctica at the end of the talk, maybe you'll feel a shiver here or there. But okay, so the evidence is clear. Our climate is changing, and it's changing perhaps most dramatically in the polar regions. And I'm going to tell you about work that we've been doing in using mathematics and physics and other areas of science to try to understand better the role of sea ice in the climate system, and ultimately to make better projections of how our climate is changing. And so in the course of the talk, you'll see a lot of pictures that I've taken. As Abby mentioned, I've been to the Arctic 9 times, the Antarctic 7 times. In fact, I was just up in the Arctic in May, a couple months ago in May, and I was in the Antarctic all fall for about 2.5 months. And the video that I'll show you was aboard this ship, the Australian icebreaker Aurora Australis. And that'll be the video that I'll show you at the end of our fall expedition to the Antarctic. Okay, so what are we talking about? Well, we're talking about the cryosphere, which is what is termed the frozen portion of Earth's surface. So in the Antarctic, the cryosphere it consists primarily of 2 main parts, namely these great land ice sheets, which are maybe up to almost 3 miles thick, and this is snow that builds up over millions of years and then gets really, really, really thick and forms glacial ice that ultimately flows, kind of like glass. If you look at a window from the side, a very old window, it might look like this because it's slowly, slowly, slowly flowing, and that's what these great land ice sheets do. And however, what we're most interested in is the frozen seawater surrounding the Antarctic continent, the ocean, the frozen ocean. And actually, the freezing point of seawater is about -2 Celsius, about -1.8 degrees Celsius, whereas, of course, pure water freezes at 0. So the salts make it a little bit harder to freeze. And so I've been very fortunate in my career to have had the opportunity to go to the Antarctic 7 times. My first time was in the Weddell Sea in my senior year of college. In fact, we were the second scientific expedition into this region since the saga of Shackleton. I don't know if you guys have heard of this. An amazing story about it's amazing that everybody survived and they were stuck in the ice for a year and it was just this incredible adventure, harrowing story. And anyway, I've been in there since then as well, since my senior year of college. And then I've also been over here in the Ross Sea in McMurdo Sound in that area. And then with the so Tasmania and Australia is like over here. And I've been off the coast of East Antarctica now 4 times. Okay, now in the Arctic, we sort of have like the geographically opposite situation, whereas instead of a continent sitting on top, because the South Pole is right about there, instead of a continent sitting on the pole surrounded by sea ice, we have continents surrounding the Arctic Ocean. So it's the ocean that sits atop the North Pole, and the great land ice sheet in the northern hemisphere is, of course, the Greenland ice sheet, which again is almost 2 miles thick of snow that builds up over millions of years and forms glacial ice. But again, what we're most interested in is the sea ice covering the Arctic Ocean, again, which is frozen seawater. So why study sea ice? Well, there's still a lot of it. It covers about 7 to 10% of the Earth's ocean surface. And as such, it forms the boundary between the 2 principal geophysical fluids on the Earth, namely the ocean and the atmosphere. And as this thin separating boundary layer, it mediates the exchange of heat. So here you see heat and moisture rising up through the ship's track of the Aurora Australis, gases, momentum, and so on. Also, the melting as well as the freezing of sea ice affects global ocean circulation. In other words, what goes on in the polar regions doesn't stay in the polar regions. There's lots of ways, particularly through ocean circulation, that sea ice communicates with the rest of the world's with the rest of the world's climate system. And, but most importantly, perhaps, is that sea ice is not only a sensitive leading indicator of climate change, but it's a key player. It's not just a passive participant in the Earth's climate system. It's a key player, a fundamental component of the climate system. Now, one of the principal roles that sea ice plays in the climate system, particularly in the polar summer, is in reflecting incoming solar radiation. Seems they all go out at the same time. Let's try the third backup. Okay, so here you have this classic white icy surface, say in the North Pole, and so most of that incoming solar radiation would be reflected because this white icy surface is going to reflect. And this is actually measured by what's called the albedo of a surface, which is the ratio of reflected sunlight to incident sunlight. And whereas the white snow and ice reflect most of the incoming radiation with an albedo up close to 1, darker ocean water instead absorbs most of the incoming solar radiation, so it has an albedo down close to 0, very, very low. And so, so as opposed to most of the solar radiation being reflected in this classic white surface situation here, if you start to lose that white surface, well, a lot of that radiation, instead of being reflected back into space, is then being absorbed by the Earth and the ocean. Now, what's made the news a lot, and one of the reasons why people are so interested in sea ice, particularly in the past, say, 10 years or so, the past decade, has been that it's melting very rapidly. This is a graph showing the extent of the summer Arctic sea ice pack at its minimum, which is in September, kind of at the end of the melt season. And this dotted line here represents about a 20-year average over the 1980s and 1990s, where most of the Arctic Ocean was covered by sea ice, even at the height of the summer. And the amount of coverage that we would observe for for most of the satellite era, long before you guys were born, was about 7 million square kilometers. However, you see there's been a general decline, and then in 2007 things fell off the table. We had a new record minimum. The extent bounced back a bit to sort of this trend line here, and then fell off the table again. And in fact, on September 13th of this past fall, 2012, the day before we left for our big fall Antarctic expedition, there was a new record minimum set. And on that day, the extent was about 3.41 million square kilometers. So if you cut 7 million in half, you get 3.5. So you can now make the statement that that over this historically very short period of time, we have now lost over half of the summer Arctic sea ice pack. So you can see how kind of dramatic what's going on in the Arctic really is. To put it in pictures and graphically from satellite images, here's a typical 7 million square kilometer ice pack in the middle of the summer back in 1979. And then fast forward now to this critical day back in September of 2012, and you see how much of the ice is gone. About half of it's gone. So I like to show pictures like this, particularly to more general audiences like you guys, because when you hear that say global temperatures have risen by a degree Celsius over 75 years or 50 years or 100 years or whatever, you know in your daily life how much temperature fluctuates, and even your own body temperature and the things that you experience. And so you might be able to just kind of write it off, like, hey, what's the big deal? Who cares? Well, when you see pictures like this, you realize, hey, there is something serious going on. Our climate really is changing. And as you can see, as I mentioned before, it is changing perhaps most dramatically in the polar regions. But this is predicted. This is what's called polar amplification. It's that the effects of climate change, and global warming in particular, are going to be predictably stronger or more dramatic in the polar regions, which is what we're seeing. Now, one of the main mechanisms that is driving this melting, actually I should go back one slide here, is remember what I said about this albedo. You know, when you have a white icy surface, that reflects the incoming radiation. And if that's gone, well, and if you're exposing a darker surface underneath it, like the surface of the ocean, you're going to be absorbing that solar radiation. So here you see all this open water now in the middle of the summer. So instead of, it's like a double whammy. Instead of ice being able to reflect that incoming radiation back into space, it's now being absorbed by the ocean, which means you warm the ocean even more, which means you melt even more ice, which means you expose even more ocean surface, which means you absorb more solar radiation, which means you warm the ocean even more and melt even more ice. This is called called ice albedo feedback. And this happens on a local scale as well. So again, you melt the ice, you lower the albedo, you absorb more sunlight, which means you melt more, and so on in this so-called positive feedback loop. And this happens on a local scale as well with these melt ponds on the surface of, say, Arctic sea ice. And I'll be saying a few things about that because we have a lot of research going on these melt ponds. I'll say a bit about it towards the end. Now, when you look at images like this, so these are photos these are both from the Antarctic. This is from the Arctic. In fact, actually, this is one of my closest colleagues, Hayo Aiken at the University of Alaska Fairbanks at the Geophysical Institute. And that person right there is Amy Heaton, who took calculus with me. So I teach these big freshman calculus classes, which I love to teach. And because I love to show people how interesting mathematics is and how exciting it is, and I like to defy people's their perceptions and their expectations that they think, oh, math is just a boring subject. Well, it's not. It's at the base of all science and engineering. Hopefully, you'll realize that hey, math is pretty cool. There's a lot it can do that you might not expect. But anyway, Amy was a freshman working in my calculus class, and anyway, she wound up doing research with me her whole, as a lot of undergraduates, working with me as an undergrad and became a co-author on various papers. And I think she was the first student that I brought up to the polar regions, actually. So anyway, when you see pictures like this, you might think that sea ice is just some barren, impermeable, frozen cap. But in fact, it is a complex, porous composite material. So when you freeze seawater, you can't incorporate the salts into the crystalline structure of the ice. And so in fact the ice tends to reject a lot of the salts, called brine. Brine is salty fluid, salty water. And so what happens is what's left over is these little sub-millimeter scale inclusions of brine, which are laced throughout the ice. And this is what distinguishes, say, sea ice from this glacial ice that covers that forms the great land ice sheets on Antarctica and the Arctic, in the sense that this is a very interesting and complex microstructure that can change dramatically with temperature. Here's showing a scanning electron micrograph showing it's really the fine structure of these brine inclusions, and these brine inclusions can link up and coalesce and form vertical pathways through the ice, channels, and then if you slice one of these channels this way, this is what you might see, this kind of very complicated, like tributary type of structure there. And I should mention that, of course, fluid can flow up and down through these channels and through the porous microstructure itself. You know, like when you, for example, like cement has some porosity to it. If you hose down a driveway or something like that, you know, some of the water seeps down into that porous microstructure, or into a sandstone, into rocks or things like that. It's very, very similar kind of behavior. Now, fluid flowing through the porous microstructure of sea ice turns out to govern a broad range of processes that are important for understanding the role of sea ice in the climate system, as well as for the ecosystems that live there. So one of the most important examples is these, as I said, these melt ponds on the surface of the Arctic sea ice. So whether or not these ponds grow and get bigger, of course, that's dark, that's light. So understanding the configurations of these the melting water on the surface of the ice is very important for trying to understand the dynamics and the physics and the mathematics of the melting, and in particular the overall albedo or reflectance of the ice pack. So whether or not these ponds pool up and grow or just disappear overnight is all controlled by how easy it is for fluid to flow through the porous microstructure of the ice. And this is, I'm referring to what's called the fluid permeability of this porous medium. And now, in the polar regions, in the Arctic Ocean and the Southern Ocean surrounding Antarctica, they have the richest, densest sea life in the world. And these complex, very robust food webs are supported by the algae that live in the brine inclusions in the sea ice. So you see this layer, that's all algae. And there's some of what they look like. Here's some algae living inside the brine inclusions. And of course, how do they get their nutrients? Through seawater, nutrient-laden seawater percolating up through this porous microstructure and effectively feeding the algae. Of course, because they need light as well, so that's kind of an interesting mathematical question. Like, okay, they need to be close to their nutrients, but they need to be up high for light, so there's kind of an optimization type of question that arises that I don't even think anybody's looked at, actually. But anyway, interesting math problem there. So, so one of the big issues here is what I call linkage of scales, namely, what's controlling these larger scale processes, such as the evolution of these algal communities or the evolution of these melt ponds, and therefore the overall reflectance of the ice pack, is being controlled by what happens at this sub-millimeter scale. So as mathematicians, we're interested in trying to develop mathematics that helps us go from information about this micro scale to tell us about the macro scale. Okay, so what does this talk about? Well, fundamentally, it's about how we are using the mathematics of composite materials and statistical physics to study sea ice structures and processes, ultimately to improve projections of climate change. You'll see there's a lot of inadequacies in the last generation of climate models. I'll tell you a little, I've already told a little bit about fluid flow through sea ice. I'll tell you a little more about that, a little bit of the mathematics of this called percolation theory, a little bit of how we are studying some of these processes through remote means and electromagnetic modeling and so on, and monitoring, I should say, as well as, of course, the experiments we do in the Arctic and the Antarctic connected to this work. And then finally, we'll take some of the ideas that we apply on these scales, on this sub-millimeter scale, to understand what's going on in the inner workings of the ice, and apply that to much larger features, such as the geometry of these all-important melt ponds in the Arctic. A couple of the key concepts: first, critical behavior, how a small change in a parameter of the system can induce very large changes in the overall or effective properties. Linkage of scales, again, how does the smaller scales influence what's happening on much larger scales? And I should say, this is one of the fundamental challenges of science and engineering, and in particular climate science. You have information on some scale, but the models that the climate models that we deal with are what would be called coarse-grained models. They're on they can only function on much larger scales. And so part of the challenge is, how do you mathematically compute or estimate or calculate the properties, the smaller scale properties, and how does that translate into larger scale behavior? Another particularly important concept that I love, and I love to tell people about, because again it challenges people's expectations about mathematics, is what I call cross-pollination, where you take ideas and methods and techniques from seemingly completely unrelated areas of science, engineering, medicine, and apply them to sea ice. Or vice versa, where we take ideas that we've developed for sea ice and apply them to other seemingly completely unrelated areas of science and engineering. And this speaks to the power of mathematics. In other words, to a person, say, classically trained in the geosciences or something, they may not realize that there's this deep connection between sea ice and human bone, for example. But for a mathematician, it's obvious. The math is the same. The physics might be different, but some of the underlying math, but even the physics might be very similar as well. But the point is that it's the mathematics, the mathematical framework, the mathematical platform that allows us to go back and forth. And finally, ultimately, in some sense, what we're, in addition to trying to improve projections of climate change, ultimately what we're really doing is trying to develop more rigorous ways of representing sea ice and climate models, which are currently represented in a very rudimentary and somewhat inadequate fashion. Okay, so I've had been able to entrain a lot of non-sea ice people, even especially at University of Utah. I mean, not the penguins here. I mean, they help out too, but There's been a lot of faculty, both in mathematics as well as atmospheric sciences, electrical and computer engineering, had a number of postdocs, different graduates, a lot of graduate students, but a lot of the graduate students that I've had started with me as undergraduates, even in freshman calculus classes, and then worked their way up, so worked with me for 3-4 years as undergraduates, published papers, and then wanted to stay on for graduate school. I've also had a lot of undergraduates through our research experience, NSF research experiences for undergraduates program. I've had about 25 or so in the last 10 years, and a lot of those I've brought to the polar regions, to the Arctic, to the Antarctic, and we have at least we have a great record. I mean, at least an 85% success rate in bringing students back, the ones that don't get eaten by the killer whales and the polar bears and stuff like that. No, I'm just kidding. We brought everybody back. Everybody has made it back safely with all their fingers. And now recently, I've started working with high school students. I have 3 working with me now. One, Rebecca Nickerson, she just got an MIT. She'll be published with me. She's, some of these, I'm sure most of you are like this, just amazing students, I have strong connections with the University of Alaska Fairbanks, all these people, New Zealand, our close colleagues in Australia, and so on. Okay. So most of you may have heard about the IPCC reports, the Intergovernmental Panel on Climate Change. And these are actually, there's going to be the next really big report about what is happening to what's the current state of Earth's climate and what do we project will happen in the future. Should be coming out, I think, toward either the fall or towards the end of the summer or something. And while all the world's 20 best climate models predict a general decline of summer Arctic sea ice over the 21st century, what is dramatic is that what we actually observe, that's the observations. These are the models. This is what we actually observe. Obviously, they're not matching up real well. What's happening is the ice is melting much more rapidly than any of these models are able to predict. And that's ultimately one of the main things we're trying to do, is to try to understand the physics and the mathematics of sea ice in order to better represent it in climate models and then improve those projections. Now, just a few words about global climate models. Global climate models, they're systems of partial differential equations. So those of you who have had calculus are familiar with what a differential equation is, an equation involving the derivatives or rates of change of some function such as the temperature or the velocity of the current fields in the ocean or things like that. Systems of partial differential equations derive from the basic laws of physics, chemistry, and fluid motion. You see there's a lot of different kinds of science that comes into play here. And they describe the state of the climate system, namely the ocean, the ice, the atmosphere, the land, and how they are interacting. And then these equations are solved on 3-dimensional grids, these big grids like this, of the air, ice, ocean, land system. But then here's the problem. With grid sizes on the order of 100 kilometers. Not 100 meters or 100 millimeters, but 100 kilometers. And that's the fundamental problem. The world's most powerful computers, the complexity of these models dictates that the best you can do with regard to resolution is like 100 kilometers. Now, I've been telling you about processes that are happening on the sub-millimeter scale in sea ice and how important they are in understanding the role of sea ice and the role that it plays in climate. And so again, this is this fundamental issue of linkage of scales. How do you upscale information about what's going on a much finer grid, and how do you incorporate that into these much coarser models? I mean, just look at that. I mean, right on this model right here, there's Florida. I mean, Florida's a pretty big state, or you can't see California there, so that would have been more appropriate. But I just gave a lecture in Florida, so. And anyway, you see there's maybe 3 or 4 grid points there. Well, there's a lot more going on in Florida, in all the different processes, than can be possibly incorporated into 3 or 4 grid points. But that's the challenge. So you want to try to predict what's going on with these rather coarse types of models. Okay. These models are very complicated. They have all different components to them, and the sea ice component, some of the main ingredients are information and how does the ice thickness evolve, because the thickness of the ice is kind of complicated in the sense that you can melt the ice, that decreases the thickness. You can grow the ice, which makes it thicker, but then you can also crunch ice together, as you'll see in the video. You can crunch ice together through dynamic redistribution, and then it gets much thicker, potentially very rapidly, even though you're not actually growing ice. So all these kinds of things need to be incorporated mathematically into these models. Balance of forces, basically F equals ma for sea ice, and then also how does heat or radiation flow through the ice. So all these things need to be incorporated into these climate models. Okay, so with all this talk about melting ice, well, who cares? Is it going to affect you? Well, I mean, if you were a polar bear, yeah, it would affect you. So certainly the polar bears care because they use the sea ice as a hunting platform to eat seals, or scientists up in the Arctic. But fortunately, we've been, actually there were a bunch of polar bears this last time, but none of us got eaten or anything like that. But actually, you would find amusing that National Science Foundation has changed their policy in that we used to carry our own guns to protect ourselves from polar bears. But of course, you're in the ice, doing your work and so focused as a mathematician or a scientist on your little project. And, and polar bears, they will cover their nose and sneak up on you, and because you're just food for them. So anyway, now we have to have a line item for what is called a bear guard. This has to be a native Alaskan who is basically very familiar with the terrain and what it's like to be up there and dealing with polar bears. And they actually have an official card that says mammal hazer. They are licensed to haze mammals, and in particular polar bears. So that means they can fire, not just shoot them, but to try to scare them away first. So there's a whole complicated protocol as to how you actually deal with these polar bears. But anyway, the bottom line is the polar bear populations are definitely being affected by the loss of all this ice, because that's how they hunt. The whales are affected. This is actually a photo from 1988. So this is off right near Barrow, Alaska, which is where we go to do our experiments, the northernmost point of the United States. And so back in 1988, this picture is, in other words, the locals tried to make breathing holes for these whales that were trapped because there was so much ice at this time of the year. And in fact, some of you may have seen this movie called Big Miracle. Has anybody seen that movie? Wasn't it pretty cool, huh? And anyway, it's all about this story of how a Russian icebreaker and the environmentalists and the oil people, they all came together to save the whales. And it was just this heartwarming story. But the problem is you won't have movies like this now. You're not going to be getting whales trapped in the ice, certainly not at this time of the year. So Hollywood is affected. Of course, you can open it up to all kinds of other different kinds of disaster movies with all the stuff that's going on and everything. So maybe it'll be a wash for them. The oil companies care about the loss of Arctic sea ice. About 25% of the world's undiscovered oil reserves are in the Arctic Ocean. And in fact, when we would go up to Barrow to do our research, it was just all scientists up there. But in the last couple of years, there have been a lot of oil workers up there getting ready to drill and stuff. So and as the ice recedes, they can drill more oil. And anyway, so things are opening up for the oil industry, and they're trying to take advantage of this as well. Now, I live in Utah, and one of the we care. In fact, it says on our license plates the greatest snow on Earth. Well, some of the computer models say that, well, you take out a huge hunk of the climate system, like the Arctic sea ice pack or some big chunk of it, it's going to affect weather patterns and storm tracks and so on. And so there's one climate model projects reduced precipitation in the American West, which certainly would affect all of us, actually. And a lot of Utah's economy is based on tourism. So these are real questions. This is not just, oh yeah, I care about the polar bears, but big deal. How does it affect me? Well, these things do affect you, and they will affect you eventually. Okay, let's talk a little about fluid flowing through the sea ice. So this is called Darcy's Law for slow viscous flow in a porous medium, where we relate how much fluid flows through the ice to like a pressure gradient. Sometimes given the pressure gradient, sometimes the fluid might go up and flood and percolate and flood the surface, or it might drain out like the melt pond drainage issue. And then the coefficient that relates the fluid velocity to the pressure gradient is this, what I would call a fluid conductivity, where the numerator is the so-called fluid permeability tensor. I mean, it could be different ability. It's much easier for fluid to flow vertically because of an anisotropy in the brine microstructure versus horizontally, for example. So this has different components in different directions, and then the denominator here is the velocity of the fluid. And so this is, so figuring out this fluid permeability is a very complicated problem in mathematics and physics. An example of what's called homogenization, which is a field of mathematics developed for analyzing the effective behavior of heterogeneous systems, which is kind of where a lot of my mathematical background is. Now, one of the most important things that I've discovered in my career is effectively the on-off switch for fluid flow in sea ice. And so, roughly speaking, when the fraction, the volume fraction of the brine phase, of the fluid phase in sea ice is below about 5%, the sea ice is effectively impermeable to fluid flow. And then for brine volume fractions above 5%, it's increasingly permeable. And then this critical threshold of about 5% corresponds to a critical temperature of about -5 Celsius for a typical bulk salinity of about 5 parts per thousand. So this is now known as the rule of fives. And it controls a lot. Such as, in fact, I discovered it by being out in the middle of a storm in the Antarctic at midnight in 60-knot winds, and I actually witnessed seawater percolating up and flooding the surface. And that was what gave me the first idea about this phenomenon. And in fact, the freezing of that slushy mix on the surface of Antarctic sea ice accounts for about 25% of the ice that's produced in the Antarctic. So it's a very important process. The evolution of salinity profiles, which is of how the amount of salt changes as you go through the ice, that's very important in climate modeling. When you have brine moving around in the sea ice, that helps to enhance thermal transport, like when you stir a coffee cup or hot chocolate or something, helps to cool it off. And also, as I've mentioned, the evolution of these melt ponds is intimately connected with this rule of fives. Also, as I said before, there's the algae that lives there. And biological activity turns on or off according to my rule of fives, because that's how they get their nutrients. That's a manifestation of the critical point in the rule of fives right there. They were growing, nutrient, seawater pouring in, convection rolls happening, all sorts of cool stuff, and then it shuts down. That was the day when they were now in ice where the switch turned off, basically. Okay, this is just an illustration of the sea ice ecosystem, namely how the killer whales, in fact, that's algae. It says, that when you have a white mustache, got milk. Well, these guys are like, got algae, because that's like an algae stain all over their little mouths. And they want to eat the penguins. The penguins live on krill, which is like tiny little shrimp type things, and then the krill subsist on the algae. Okay, so why is this rule of fives true? Well, one of the main mathematical tools that we use is called percolation theory, the mathematical theory of connectedness. So we start, say, with a lattice like in 2 dimensions, and a bond is open, meaning it's black here, with probability p, like a weighted coin. It's closed, which are you don't see them, with probability 1 minus p. So when p is about 1/3, well, you see these clusters here, but there's no connected pathways. So fluid can't drain through there, or electricity can't flow. But now at p equal 2/3, this is a permeable state. There's a connected pathway. And it turns out that the critical threshold, the p, the smallest p for which, if we are in an infinite lattice, where we have an infinite connected cluster, turns out to be exactly 1/2. And we might call this a tipping point for connectivity. But now you might ask, well, okay, so these simple lattice models, you see the critical threshold is at 50%. And if you look at the corresponding 3-dimensional model, it's at about 30%. But sea ice, I told you the threshold is around 5%. So what gives? Well, this is a beautiful example of cross-pollination. Somehow I recalled in the recesses of my brain when I had studied a lot of material science that the microstructure of sea ice with pure ice platelets surrounded by these brine inclusions is very similar to so-called compressed powder microstructures, where you take big polymer spheres and little metal or carbon black particles and squash them together and basically create materials that absorb radar. And in fact, these are the kinds of materials that are used in stealth technology. In other words, this is the kind of stuff that they coat the B-2 bomber with, even the helicopters that were used in the raid on bin Laden's compound in Pakistan a couple of years ago. So in other words, to evade the radar. And so basically all I did was I realized that these two microstructures were exceedingly similar. I took a mathematical continuum percolation model developed for these compressed powders, applied it to sea ice, and out popped this 5% value. So we were able to theoretically predict it, which then explained all kinds of biological and climatological data. And as a result also of this connection, sea ice is a radar absorbing composite itself. It's very different. That's one of the reasons why measuring the thickness of the ice is so difficult. Radar waves just get absorbed, or radar waves of the frequencies that satellites use just get absorbed. So this is one of the holy grails of climate science, is to figure out ways to getting the thickness, to getting large-scale information about the thickness of the ice. Okay, so the next step, though, after we established this threshold, was to figure out how does the permeability change with temperature or brine volume fraction. So this is the cover of Geophysical Research Letters, and again, I kind of consider this like homogenization in action. How does the small scale stuff, this is some of our X-ray tomography of the brine inclusions, how does that control these larger scale processes such as the evolution of these melt ponds? Here you can see some of this evolution of the conductivity of the brine phase. And again, I conjectured this rule of fives back and the reasons for it back in 1998, but it took another at least 10 years or so to develop this X-ray tomography method, and so we could really sort of quote prove my rule of fives. So here we have no pathways, one pathway, many pathways. So we take this 3D X-ray tomography data, we map 3D images of pores and throats onto 3D graphs of nodes and edges, and ultimately we can confirm this rule of fives. And then we use a lot of lattice and continuum percolation theory and solid state physics and other areas in theoretical physics to actually come up with a deceptively simple formula for the fluid permeability, the vertical component of the fluid permeability of sea ice as a function of brine volume fraction. So there's what's called there's the 5% right there, that's the threshold. And then there's a 2 that's called a universal critical exponent, which actually holds for lattices, but it's kind of amazing that it actually holds for a real material like sea ice, but we can actually calculate that out and show that that's supposed to be the case. And then also this constant in front, we actually compute that. It's not just a fudge factor that we stick in to fit the data, it's something that we compute from our X-ray tomography data. And we use a theory called critical path analysis, which are another example of cross-pollination, originally developed for electronic hopping conduction in doped semiconductors, like the kind of semiconductors that are in your computers. And we take that and, again, apply it to sea ice. And so here's a nice comparison between our theoretical predictions. There's a theoretical prediction, and then here's like the statistical best fit of this data. And we have a lot more other types of theories like this that do quite well. Okay, how do we monitor all this? How do we try to remotely study these transitions and processes in the sea ice? And this is where we get into the issue of remote sensing, where basically you have like a satellite up in space bouncing microwaves off the surface of the ice, or helicopters or so on. And ultimately this is what's called an inverse problem, where we would like to recover the properties of sea ice from bulk electromagnetic data that we get from radar or microwaves or other types of electromagnetic radiation. And the key parameter is called the effective complex permittivity, which describes the effective electromagnetic properties of the sea ice. We're ultimately interested in recovering ice thickness, ice concentration, the volume fraction of brine, how they're connected, and so on. And again, this is really the topic of homogenization, or even in the case going backwards, like inverse homogenization, where say we have a two-phase material here, conductivity sigma 1 and sigma 2. We want to then step way back from this and look, if we look very, very far away, well, it's kind of gray. You don't see the individual inclusions. And then our job as mathematicians is to compute the effective conductivity of this composite. In other words, find the homogeneous medium which behaves macroscopically the same as that inhomogeneous material. And this problem has a long and illustrious history going back to Maxwell himself, who developed Maxwell's equations, which were basically the basis of light and radar and any kind of electromagnetic phenomena. He first computed the effect, or tried to leading order, the effective conductivity of a dilute suspension of spheres. And another very famous scientist that I'm sure you've heard of, a guy named Einstein, also worked on this problem, where he computed the effective viscosity of a dilute suspension of rigid spheres, kind of like this system here. Okay, so some of the math that we actually use in this involves complex numbers, because fundamentally the parameter that we're interested in is a complex number, involves the number I, which is the square root of -1. And so forward homogenization problem is where we have information about the composite geometry, which we incorporate into a mathematical object called a spectral measure, which if any of you have studied linear algebra or matrices, there are these things called eigenvalues and eigenvectors that basically give you most of the important information about a matrix and array of numbers. And anyway, then we can get all sorts of very sophisticated information about the effective electromagnetic properties of the sea ice, and then we can turn that process on its head and do inverse homogenization, where we are given effective electromagnetic data and we invert that to obtain information about, say, the Brownian volume fraction, the conductivity, and so on. Now here's another example of cross-pollination. The methods that we have developed for sea ice, because of the fundamental similarity of the composite, the porous microstructure of sea ice and human bone, we have taken our methods for sea ice and applied that to understanding and characterizing the conductivity of human bone, ultimately to develop new ways of electromagnetically monitoring osteoporosis and the loss of bone conductivity. In other words, and that's again the beauty and the power of math. The math doesn't care if it's sea ice or bone or lungs or brain or wood or metal or whatever. If the math is the same, you can take it wherever you want. We've also been, again, now looking at this linkage of scales, trying to compute these spectral measures in these kinds of important quantities for the whole Arctic ice pack. Here you see these are the first calculations like this. And anyway, I won't go too much into that, but it's helping us try to understand, to develop this more rigorous pathway for incorporating sea ice into climate models. And then, so as I said, we've done a lot of experiments in the Antarctic and the Arctic, where essentially we're developing electromagnetic methods of monitoring fluid flow and microstructural transitions. And we've made extensive measurements of fluid and electrical transport properties of sea ice on all these most recent trips in the past few years. This is actually the cover of the notices of the American Mathematical Society, where I like to call this, I'm measuring the fluid permeability of sea ice in the Antarctic ice pack. And I think I believe I'm the only living mathematician who's been on the cover. They usually only put dead ones on there, so I'm hoping that's not a harbinger of, Anyway, because I've been in some pretty dicey situations particularly the Antarctic, but. Anyway, I like to call this my $1 million meter stick, because all my friends there have all these multi-million-dollar instruments, but I was using a meter stick and my watch. That was and in fact, I like to call what I do Home Depot science, because so much of what we actually use, I just buy it at Home Depot. It's a pretty cool place. I love Home Depot, Abby. Next time you need, I'll go there. One of the cool things we found is that we have a much higher percolation threshold in the fine-grained granular ice that dominates in the Antarctic. And we've actually really nailed that down on our last trip. This is some of our setup for some of our electrical measurements. That's the Aurora right there. And anyway, we were the first to actually extract these ice cores and put the electrodes like this. All the previous ways of measuring the conductivity properties of sea ice, the vertical and the horizontal were all mixed up. But we were interested in relating the vertical permeability to the electrical conductivity, so we extracted ice cores and then directly measured the vertical conductivity. And then as a result, we were able to, after people studying this for 50 years, we had the first measurements and theory of this on-off switch of my rule of fives. And so in other words, here's data from the Antarctic, and this same beautiful theory that we developed for permeability of the ice. Okay, then finally, I'm going to show you did this turn off or something? I'm going to, in a minute, I'm going to show you the video. I first want to this last little bit about sort of the multi-scale structure and the fractal. How many of you know about fractals, have seen fractals? Okay, good, that's good. So this is a fractal here. These are fractals. These are the so-called Sierpinski gasket. And let's see, so sea ice displays composite structure on like length scales about over 10 orders of magnitude. The submillimeter scale, the polycrystalline scale. This is kind of like what metals look like, polycrystalline structure. These are the brine channels. These are really big brine channels in the Arctic. When I look at this is pancakes forming in the Southern Ocean. I view this as a composite material. Now we're moving up in scale, up. and then all the way up to satellite images, where again, I view this as a two-phase composite of ice and water. And again, we're looking from space. Did you need to do something? Oh, let's see. No? It's not doing anything. Okay, well, all right.
Well, this one looks like.
Okay. Anyway, so here's some of these melt ponds on the surface of the ice. You see this beautiful geometry. You know, if anybody's interested in geometry and mathematical geometry here, you can see there's just, you know, these are fabulous pictures, I think. Am I okay?
Yeah, I think it's.
Okay. I think they can hear me now. Okay. Okay, so there has been a lot of work on trying to develop numerical models of the evolution of these melt ponds. Very detailed partial differential equation models, which ultimately are being incorporated into climate models. But we stepped back from this problem and asked different questions that nobody had ever asked before. Namely, are there universal features of the evolution similar to phase transitions in statistical physics and the kinds of mathematics and physics that I've just been talking about on much smaller scales? So here's just one little slide on fractals. So these are not fractals. These are simple curves, simple Euclidean curves. This is a line is a one-dimensional object. You start bending it up so much, you get this Koch snowflake, which has a fractal dimension of about 1.26, and then all the way up to space-filling curves, which are curves that move around in the plane so much that they actually fill space, and they have a fractal dimension of 2. That would be, if you're in the plane, that would of course be the largest dimension that you could possibly have as a curve. And anyway, motivated by some early work of Lovejoy on the fractal properties of clouds, he analyzed area perimeter data and found a fractal dimension of about 1.35 for clouds. We thought we would see something very similar for sea ice, but we in fact found something much more interesting, where if we plot, we analyzed hundreds of thousands of melt ponds. If we plot perimeter data versus area, so this is on logarithmic scale. So the slope here is the fractal dimension. And you can see the slope changes at around this critical length scale here. And then it's flat, and then it steepens up. And anyway, that data point right there is a simple Euclidean pond. That point right there is a transitional pond. It's trying to become self-similar and trying to become a fractal. And then that pond right there, this is a well-developed, highly complex pond with a boundary that's trying to behave like a space-filling curve. This is a graph that we were able to compute showing how the fractal dimension transitions from 1 all the way up to 2 around a critical length scale of about 100 square meters. We also see a percolation phenomenon on this large scale. Namely, here's individual melt ponds. They coalesce. They start to form pathways just on the scale of the image, and then they dominate the image. We've developed a lot of starting to develop a lot of mathematical models, such as, here's a random surface, and this is work with Brady Bowen, who's now a sophomore, a double major in math and physics at Utah. And if we take, this is like intersect that surface, that random surface with this plane, and then you move that up and down, and the configurations that you get look just like melt ponds. And this is another example of cross-pollination. These methods were originally developed in the context of diffusion and turbulent plasmas and electronic transport in disordered media. Again, completely different area. And this is some of what our model melt ponds look like. And then all of this, then here's where they percolate. Now there's a pathway through there. And this model exhibits this transition in the fractal dimension. We've also taken what is widely known as the most widely studied model in statistical physics, a model called the Ising model for ferromagnets, which is actually studied a lot in the math department here at Davis, actually by some really world experts here, where basically the warmer we make it, the more these things look like melt ponds, basically. But here, the melt ponds are clusters of magnetic spins that align with an applied field. So again, seemingly completely unrelated, but we've adapted it to the melt pond problem for sea ice. Okay, so I'm going to show you, I'm sorry I'm going to run a few minutes late. I'm going to show you the video in just a second now. So in conclusion then, the summer Arctic sea ice pack is melting rapidly. Fluid flow through sea ice mediates many processes of importance to understanding climate change and the response of polar ecosystems. We've been developing mathematical models of composite materials and statistical physics, ultimately to help unravel the complexities of the structure of sea ice, and hopefully to provide a more rigorous path toward representing sea ice in climate models. And part of my own point of view is that field experiments are essential to developing relevant mathematics. It's one thing to sit in your office and speculate about how a terribly complicated system like that is behaving. It's completely another thing to go down there and see it for yourself. It changes the course of the questions that you ask. And finally, our research will help to improve projections of climate change and the fate of Earth's ice packs. And I have to thank the National Science Foundation, the Office of Naval Research, and a lot of other organizations and countries for help, for funding. Also, I want to point out we have this Math Climate Research Network. So this is precisely for you kinds of guys. This is a 5-year, $5 million project that we have from the National Science Foundation with hubs all across the United States, specifically geared towards bringing young mathematicians into climate research. There's so much expertise out there in the mathematics world where people don't realize that, oh my goodness, I have the kind of expertise that is required to solve this really hard problem in climate research. And this grant is designed to do that. So now I'm going to show you the video. And again, I'm sorry I'm going to go a couple minutes over, but so the video takes place on the Aurora Australis, which is the main Australian research icebreaker. And so my first time with the Australians in 1998, the ship caught fire. About 2:45 in the morning, we had just been out, well, we'd been out at midnight on our first little expedition out on the ice, go to sleep for about an hour, then the alarms start going off. Please don't be alarmed, but we have an uncontrolled fire in the engine room. Not exactly what you want to hear when you're in the Antarctic ice pack, where you know nobody's going to come and save you. 10 minutes later, please don't be alarmed, but we're lowering the lifeboats. Particularly not what you want to hear as a mathematician. Like, what am I doing here? I prove theorems for a living. Anyway, obviously I'm here. We survived. There was a lot of cool media coverage, like icebreaker burns, fire and, all that kind of fire and ice imagery. That, anyway, we got T-shirts to commemorate the occasion. Okay. Anyway, with that, let me now show you the video. So this is from our most recent one in the fall. Okay, I think we need the sound up a little bit. I think we're okay, actually. Okay, so these are just a few opening scenes for Wet Your Whistle. You'll see a lot of these waves and stuff. That's one of my favorite things. So finally, we're back in Hobart. I think we did the fastest after being 2 weeks late. I think we did one of the fastest crossings across the Southern Ocean, like 4 days flat or something. It was pretty amazing. So anyway, thanks very much for your attention.